If you try to build an enterprise AI system by plugging a search API into a standard chat prompt, it is going to break. The problem arises when you force a large language model to do everything at once. When it has to manage the control flow, execute external tools, and synthesize data all in the same breath, the model runs out of working memory. It starts forgetting its instructions, leading to severe context degradation and endless hallucination loops. Even when the AI manages to produce an answer, the output is usually a messy, unpredictable block of text. The moment that unformatted natural language hits your downstream business tools or a relational database, it shatters, because these systems require strict structure to function. This fragility makes basic chatbots completely useless for high-stakes environments. You cannot run an algorithmic trading system or an enterprise business intelligence platform on software that occasionally invents numbers. To survive in a production environment, organizations have to stop treating AI agents as conversational chatbots. Instead, they need to be rebuilt as deterministic, distributed systems, governed by strict, inflexible rules. This brings us to a concept called the fixed research script. Instead of letting the AI organically guess its own path, we replace its free-form thinking with a rigid state machine. A state machine is a mathematical model of computation that dictates exactly what status a system can be in at any given time. A central workflow engine takes absolute control. By stripping the language model of orchestration duties, the engine dictates precise state transitions and retries. Moving down, it directs a lead researcher agent, which spins up a swarm of specialized sub-agents to handle tasks simultaneously. This parallel search swarm is intentionally designed to completely bypass the memory limits of any single AI model. It allows the system to gather massive amounts of raw data across the open web and internal document stores, all at the exact same time. Behind the scenes, every single message and tool call is logged with a trace ID. Trace IDs are unique alphanumeric tags assigned to individual operations, so engineers can replay failed executions and debug complex transitions. By separating the logic of the workflow from the language processing, the system gains native retries. If one specialized agent fails, it doesn't corrupt the entire global research cycle. Once the search phase finishes, the parallel swarm returns with a mess of raw HTML and PDFs. All of that unstructured data has to cross an absolute boundary, the data schema, which instantly slices the raw text into clean, structured JSON. There is a strict rule at this stage: extraction agents do not summarize. Summarization completely destroys the underlying granularity of the data, stripping away the precise mathematical details that algorithmic systems rely on. Instead, these agents are forced to only extract specific atomic claims and isolated numeric values. This table shows why structured outputs must be rigorously version controlled. Removing or renaming fields breaks compatibility and causes immediate downstream system failures. Looking below, the pipelines safely handle schema evolution by making new data fields optional to guarantee backward compatibility. Enforcing these typed schemas at every boundary ensures data consistency. It creates a filter that instantly rejects AI hallucinations and formatting errors before they can ever contaminate your primary data warehouse. After extraction, the schematized data is split into an AI feature store. This prevents our agents from wasting computational power and money by constantly rescraping the web just to find historical context. The data is divided into two distinct homes. The semantic embeddings of the raw text go to a highly scalable vector database, while the discrete, verifiable facts are sent to a relational SQL database. SQL is a standard programming language used for storing and retrieving data in tabular form. For final synthesis, the system uses a multi-agent debate pattern. One synthesizer agent drafts conclusions, while a separate critic agent actively tries to poke holes in it, searching for mathematical errors or logical leaps. The system only moves forward when they reach perfect consensus. This rigorous debate, combined with deterministic SQL grounding, ensures that the final intelligence object is mathematically verified and completely stripped of any individual AI's confirmation bias. This dashboard shows the destination of verified intelligence. Structured data flows directly into an enterprise business intelligence platform without manual modeling. Scanning the timeline, populated fact tables automatically track dynamic, real-time shifts, like unexpected competitor product launches or sudden executive leadership moves. Because the entire pipeline is highly observable and rigorously evaluated using automated LLM as a judge frameworks, these data signals can actually be trusted to trigger real-world actions. LLM as a judge is an evaluation method, where a secondary language model is used to score and verify the accuracy of the primary model's outputs. The concrete business impact is immediate. Detecting a subtle pricing shift on a competitor's website can instantly update a prediction market trading bot, or autonomously trigger a highly personalized, localized go-to-market email sequence. The future of enterprise artificial intelligence simply doesn't rely on writing a clever chat prompt anymore. It requires engineering a strict, industrialized data pipeline that takes chaotic, raw information and reliably weaves it into structured intelligence.